Good morning, good afternoon, or good evening, depending on where you are. My name is Colin Genge from Retrotec Inc. We do our manufacturing in Everson, Washington, USA, and I just happen to be in Canada right now as we speak. So I hope this is going to be an informative and exciting session for you. And we're going to be talking about new testing opportunities with the equipment you already own. So I can find out what equipment you own if you can just list what you own in questions. Just trying to see how to advance these slides here. Hello. Tools in terms of smoke buffers, digital pressure gauges, blower door, flow hoods, duct testers, infrared cameras, etc. Just list what you have and put it into questions, and I'll see them. I recognize they're not really a question, but and yes, Mo, the session has started. So this will give me a little bit of an idea as to what kind of equipment you have, and hopefully I can adjust the presentation slightly to suit, which would be great. I see we've got a pretty good audience on hand here, and I'm starting to get a list is popping up of all the equipment that you have. Someone said, oh, got an anemometer, I guess barometer, thermometer, humidity gauge, what the heck. A really great resource that we have on our website under support is a whole series of manuals that you can access, and they're all free, and some of them have got 60, 80 pages in them and so on, and they're definitely worth taking a look at. There's a lot of free information in there, so we welcome you to access that and use it as a resource. So as far as new applications are concerned, a couple of points. One is that you should be sticking with an area of expertise that you have, areas that you have training in, and so on. And if you see applications for new products, you might slowly move into them, but certainly focus on what you know and add services with the products that you have or with the testing equipment that you have already. And another really key thing that I want to stress is that you need to develop strategic partnerships with other people that do different types of testing. They might be engineering companies or other testing companies and so on. I know that a lot of you might think of your competitors as people that you always want to beat competitively, but in a lot of cases your competitors can actually work with you. In fact, this test here is of a very, very large, I think 1.2 million square foot warehouse. And I believe that several companies got together to do this to everyone's benefit. So there's a lot of reasons that you can work with your competitors, with people that are closely associated with the type of buildings that you work on. I believe that the field that we're in, we're barely scratching the surface in terms of what we can do. I know in the U.S., for example, in a lot of states where there's codes that require certain tests to be done, in a lot of cases only 10 or 15% of those tests ever get done, and people find ways of getting around it or saying it can't be done or whatever. So there's a huge amount of a market out there, and I think it's time that people in their industry started working together to develop that market to its full potential. One of the first ones that I'm going to talk about is compliments of Phil Emery of Neudorfer Engineering, who happily shares some of the new applications that he comes up with. And I'm using some of his slides here, giving him credit for it and so on. And he's using one of our fans to both measure the underfloor air distribution leakage and show where it's leaking. In this case, he's blown a bunch of smoke down there, and we're seeing it's leaking up everywhere and so on. So you may not be aware of this particular application. In a lot of cases, you might be just walking past an application that's just waiting to happen, and you don't know about it. So if you ever see someone that has a need for this type of thing, or it's part of another job that you're working on, then you can keep your eyes open for underfloor air distribution testing. In the neighborhood of 0.15 CFM per square foot, similar to what we're testing buildings at, 12.5 pascals, that kind of thing. Here he's got his fan mounted in a box, and he can flip it over and he can actually test it in both directions. And we have another shot here of an infrared shot showing what's going on under the floor. So there's a whole market there. The other one that you also may not be aware of is the whole area of refuge. Critical care is another application. Area of refuge, there are several standards on there, and whenever you have an industrial plant, an offshore platform, even a lot of high-rise office buildings or apartment buildings will often have a requirement for areas of refuge, and your local codes and so on are a good source of finding out about this, something you should look into. And all that an area of refuge is in the event of some disaster, a fire, smoke event, or whatever, if people can't get out of the building, they need to go to one of these areas of refuge. Now, in plants, industrial plants, where there are chemicals there and so on, you want to go into an area that is relatively airtight, and that's where you come in, is measuring the airtightness. And the airtightness requirement for these is very, very tight, around 0.1 CFM per square foot, or I should say 0.1 air changes at 50 pascals, about 6 times tighter than a passive house. So if you're measuring one of these, you probably want to use an aluminum frame. Our new aluminum frame does a great job. It's got a very, very small amount of leakage, and it's the kind of thing that you'd want to use to measure these very, very tight rooms. The other one is critical care facilities, and there they have a slightly different requirement. Often with critical care, they are pressurizing one zone versus another. And the next one is component testing, individual doors, fixtures, windows, and also control room pressurization. If you have one of our Model 300s, it has the capability of going all the way down to, I think, about 15 thousandths of a CFM. That's 0.015 CFM. Very, very small amounts of airflow, literally the size of a pinhole or less, that can measure. Very great application for production line. We use them on our own production line for measuring the leakage of our individual components, and we've managed to get the shell leakage of our Model 300 down from about 2 CFM at 50 pascals to about, I think, 0.01. Or no, I'm sorry, 0.009 CFM is maximum that we have it at now, simply because we can measure it. So going low is no problem. It has its own things to learn, and you're doing things at a very small scale. So they could be doors, they could be fixtures, they could even be materials. Control room pressurization goes along with zone pressurization, and some people actually specialize in doing control room leakage tests, and the reason why you would do that is they need to supply clean filtered air to these zones, and by measuring the leakage they can keep the amount of clean filtered air down to an absolute minimum. So let's just take a look. So here's an example of doing a window test. We've got a flux duct attached to plastic and red tape around the frame, so we can measure window leakage. So this would be an example of one component. This is an enclosure integrity test where a heavier than air agent is used to put out fires. They're called clean because they don't create a mess. And it's one of our specialties, and just about every large commercial building has at least one of these zones in there. They're often protected with a bunch of red bottles, and when the system discharges, there's a requirement for what's called an enclosure integrity test for two purposes. One is to determine how long the agent will stay in the room, and the other purpose is to see how much pressure is created. And in a slide that I have here, I'll show you what happens if too much pressure is created when the system discharges. Here the wall has been displaced by about half a meter, foot and a half. When the system's discharged, it's created a huge pressure pulse. The door fan test or blower door test will measure the leakage of the enclosure. The software will predict the amount of peak pressure, and so they can install the proper pressure relief vent in order to prevent this kind of damage. In the US, the standards have changed where we did not require a peak pressure evaluation. Now we do, and it's taken us a couple of years of publicity to get about a 30-40% market penetration. That means people that were doing hold time evaluations are now starting to do peak pressure evaluations. And I often think that the peak pressure damage that will be caused even during an accidental discharge may be more significant than the fire risk that was there, which is probably minimal in the first place. So that's a new application. Just backing up here a little bit, this is what the equipment looks like. Looks very similar to what you have already. This is one of our deluxe systems that allows you to measure the pressure or the leakage rate difference between the below ceiling and the above ceiling leakage areas. And this does this by pressure neutralization. We have an automated system on our gauge that will do that, so that the fan in the middle here or up top is the one that's measuring the room leakage, and the air going through this big flex duct is merely creating a neutral pressure across the suspended ceiling so that the leakage of the room can be measured independently. And this concept was borrowed from the idea of measuring apartments side by side and finding out what the leakage is between the apartments and neutralizing that so we can find out how much leakage there is to outdoors. Now, the other thing that comes up with enclosure integrity testing is that I've seen very small enclosures where the contractor spent an entire week trying to get it sealed. They're using the wrong kind of materials, the wrong kind of techniques, and so on. I think this is a very profitable service that can be offered. The value of air sealing with for these enclosures is much higher than it would be for people who are used to working on houses. It would be quite common that an air sealing job on maybe a 200 square foot room would perhaps go for $5,000 perhaps, but it means that you have to use specialized materials and some specialized techniques. And here we have somebody who's spraying rubber over rock wool, and it provides a fireproof and flexible connection at the ceiling to wall joint, which is the main culprit for leakage in these enclosures. So I think that's a very profitable business. There's a company in New York City that does nothing but this spray rubber installations in fire enclosures, and all the fire suppression companies hire them. Very easy to find that work because all you need to do is look in the phone book under clean agent suppression systems, well, if phone books existed, or track them down online and knock on the door and say, hey, I provide air sealing services, and so on, and this is this is what I do. So I think that's a very valuable surface that people can branch out into. This is just touching on, I'm sure that you infrared folks know that using a blower door with your infrared camera improves its performance remarkably. So this is an enclosure with the blower door turned off, and this is the enclosure with the blower door turned on. So you can see quite a dramatic difference there in terms of leakage. So if you have any questions along the way, I will try and answer them. Now, someone was asking me about the spray rubber. There are several companies that make it. One is Rector Seal. They're in Texas. R-E-C-T-O-R Seal in Texas. I should have had these on the screen, I guess. Another one is Specified Technologies, which are actually in Canada. Another one is W.R. Grace, and Hilti also have a spray rubber material, and I believe that 3M has one as well. They all require a high pressure pump and spraying outfit to distribute the materials, but it's an absolutely incredible material and one that you will find an enormous number of applications. There are certain things that I don't think that can be sealed in any other way. We may not be aware of this, but whenever we're using hard sealants, when the building moves, as it does, under even people load, floors can move a 1/4 of an inch or so, and a lot of conventional sealants will just crack and get pulled out. The spray rubber material, because it goes over a wide area, will take that flex. Now, someone asked a question about some of these testing techniques. In the manuals that we have online, there's a lot of these procedures are outlined, and I'd request you go there and you just take a look through the table of contents, and you'll see a lot of these of this test methodology. So passive and active smoke systems. We've been in contact with this through the whole fire suppression arm of our business, although with enclosure integrity and clean agent systems, we're dealing with a small enclosure in a large building. With passive and active smoke systems, we're dealing with just the reverse. We're dealing with the whole building, and particularly floor to floor. One of the things that we notice when we start doing a lot of blower door tests in large buildings is that there's a lot more leakage between floors than there's supposed to be. So a typical active smoke system is pressurizing the floor above and the floor below, as seen in the picture on the bottom right hand. And if there's too much leakage, then the pressurizing fans can't possibly keep up. So doing a blower door test and finding out whether or not the active smoke control system can actually maintain the required pressures is important. And then tracking those leaks down and sealing them is also important. So in all cases with these applications, it's find a hole, seal a hole, apply a pressure, see how much airflow there is, and so on. And this is certainly true with active smoke control systems. Now with passive smoke control systems, we're not relying on a pressure sandwich, I guess, to contain the smoke. We're relying on the fact that the floors are sealed from one to the next, and it's that is supposed to keep the smoke from going up through the building. Well, as we know, if we've ever seen one of these buildings when they're on fire, the smoke goes everywhere. Part of the reason for that is that the floors are not tested, and it's quite easy to do what we call a sandwich test. So we put a blower door on, let's say, floor 9 and another one on floor 10. We can actually measure the leakage between those floors. We can find the leakage paths and so on. So that does represent a whole business, a whole specialty that people can get into. Now, this is obviously not a complete training course on how to do all this stuff. It's just kind of like opening your eyes to some possibilities. One of the things that you discover when you're looking at this smoke control is certain building features which could very much assist the containment of smoke are built in such a way that they don't contain smoke. Like this is a typical elevator lobby. We have an elevator here and a relatively small lobby around the elevator. An ideal way to enclose the elevator, because the elevator is a vertical shaft that connects one floor to the next and is one of the primary ways that smoke moves. In this particular case, and probably in most cases, the walls go up if you look above the suspended ceiling, and they stop right above the suspended ceiling. This is where the smoke goes through. So it would be very easy in this design to simply run the wall all the way up to the slab and to fully contain the elevator lobby and to put in the appropriate dampers in that wall so that when there was a fire event, they would close and smoke would not be allowed to percolate right through the building. This is a passive house setup. We've got a small window frame mounted in a window. A special frame that we've devised, as you can see, it's got square corners here. So the frame itself is only about 1 or less square inches of leakage. All the frames we make, we measure the leakage of each one. And the older frames were running around 3.5 square inches, which when you're dealing with, say, a passive house at 0.6 air changes an hour, that's a total of 30 square inches. So your frame could be more than 10% of that. If you're dealing with one of the zones that we talked about earlier, where you're looking at 0.1 air changes per hour, then the frame could be a huge amount of the total. In some cases, you may even want to put a piece of plywood into a doorway or a window or whatever, tape it in place and put a hole in it, and then mount your test fan through that. So if you've got any questions as we go, I'm not seeing any here unless they got buried in the part where people were describing what products they have or what testing instruments they have. Now the next one is what I call pressure mapping and diagnostics. I probably didn't put enough pictures in here for this one, but we did write an article recently for NEBB magazine, and we talked about how you can go around a building and map the pressure in that particular building. And if we have time, I'll show you another slide I developed for a presentation I'm doing next week that will demonstrate a problem that is very common in, I call it medium-rise office buildings, where the pressures from floor to floor are really imbalanced, so that there's a lot of losses. So I'll get onto that a little bit later. This is rain penetration testing, and here this gentleman has installed a spray rack on the outside of the building, and they're going to spray water all over this wall section and use the same fan that we use for measuring leakage for simply applying pressure. This particular fan, which has the variable frequency drive, as you can see down here, is particularly adept at creating tons of power and can give us 300 pascals in a room in order to detect the rain penetration paths. Any of the things that we talk about here, you can get. Someone asked if the small window frame is available in Europe. Absolutely, no problem. It's a pretty recent product for us, so they haven't had it in stock for a long time, but the new aluminum frame corners that we have allow us to cut aluminum frames square to any length that we want, so that we can reattach the hardware and make frames of any size. So we've made a smaller window frame, and it is actually possible to take one of our big frames and cut it down and make it pretty much any size you want at this stage, because all the corners are now square cut. They're no longer mitered. So here we're watching a roof membrane test. There are people that do this under positive pressure, under negative pressure, and so on. This is something that the commercial duct tester that we have that's capable of going up to 20 inches of water, 5,000 pascals, can do quite admirably. It can create positive pressure or negative, and that would be another avenue. I can't say that I'm any kind of expert on how to test room membranes. I just want to point out that it's a possibility. So here we're talking about a test method for testing individual apartments and finding out how much they leak on all the 6 sides. So it's quite easy to find out what the total leakage is on all 6 sides, but finding out what it leaks on each one of those sides is a little bit more difficult. And this is how we do it. I'm sure many of you have seen this before. So here we have one blower door testing one apartment at 50 pascals. We've got the doors and windows open on the adjacent apartment, so we can allow the leakage to occur on all 6 sides. So in this case, we have a total 1,200 CFM, 1,200 cubic meters per second, whatever it is. It's just a number. So we're measuring the total leakage on all 6 sides. In the next slide, we're going to be measuring by inference the leakage from the apartment to the hallway. And how we do that is we put another fan into the stairwell and we pressurize the hallway to 50 pascals. And in the manual, by the way, we show you exactly how to hook this up if you're interested. And here we are measuring 1100 CFM, so obviously this wall across here, which has now been neutralized, was leaking 100 CFM. So we've been able to, out of the total of 1,200, we've determined where 100 of it is coming from. The hallway to apartment wall, this one right here. In the next one, we simply open the door to the adjacent apartment with the windows closed. The pressure from this fan goes in through the door. This is set to pressure, so we've now neutralized the pressure across this wall. In this case, the flows drop down to 900 CFM, and we can similarly do the same thing by opening the door on the other side, neutralize this wall. We see the flow in this fan drop. We know what this wall is leaking between these 2 units. And we can similarly, by applying another fan to the floor above, see how much leakage there is from floor to floor. Often in occupied buildings, we can't get the opportunity to test the entire building, but we can get an idea just by taking one corner of the building, or say 2 or 3 apartments in one part of the building. We can get an idea of what kind of leakages we can expect in other parts of the building. Typically what's happening in one part is probably kind of similar to what's happening in the other part. Leakage from floor to floor can vary to being major to unmeasurable. And even in concrete slab buildings that you would think there's no leakage between floors, sometimes what we measure is something fairly significant. Someone was asking if you can get those corners for your normal frame. There may be no reason why you can't just cut the ends of your frame off square and put the ends in there. I'm not sure you want to go that far, but you could theoretically do that. We've changed not only the corners, but we've also changed the expansion mechanism and all the different parts. So I don't see why the corners couldn't be made available. So you could ask about that. So the next one is pressurized stairwells. We often get jobs to measure stairwell leakage. And the reason why we're measuring it is that the client wants to pressurize that stairwell and doesn't know how big a fan to buy. So they could be buying 500 CFM, 5,000 CFM, who knows how much flow they need. Typically what they do is they oversize it, which means they've got a fan that's too large and inefficient and takes up too much space and so on. So to optimize the size of the fan for pressurizing a stairwell, you simply come along with your blower door, you turn it on to the specified test pressure, and find out how much flow is needed. In some cases, the specification may require a certain number of doors opening and so on while the fan is running, and you can do that. Other standards, there's an FBA standard for this that requires a test of the doorways to find out what the how much pressure is required to open the door. So we charge roughly around about $5,000 to do a pressurized stairwell evaluation, and it takes us about 2-3 hours, plus a little report and so on. So it's actually a very lucrative way of providing a service. It's much cheaper for the client to do that than it is to guess at what size of stairwell pressurization system to put in. Now, as far as the frames are concerned, my comment about making changes, they're not very expensive, really. So they're something that you can just buy as an added item and use your other frame for other purposes, perhaps. So now, going back to, we're talking about the spray rubber material. Spray rubber is one of the few things that you can actually use to seal shafts from the inside, because you can spray it over all manner of different surfaces. And there is a connection between elevator shafts and rooms that are attached, or units that are attached or adjacent to the elevator shaft. In some cases, you can actually feel a small pressure pulse when the elevator goes up and down. There's two things that you get rid of here. One is you get rid of the connection between the elevator shaft and the unit, which will affect energy, air quality, and so on, but also reduces the noise dramatically that the elevator makes in the unit itself. So there's two benefits to disconnecting the elevator shaft from the adjacent units or apartments or offices or whatever. But when we're talking about shafts, there are several main types of shafts that run through buildings. They're ventilation shafts or services shafts, electrical, plumbing. Sometimes they run them together. People who work on these high-rise buildings will typically block them at some point in the building. You don't have to block them at every floor, but for four-story building, if you block them halfway, you dramatically reduce the amount of airflow that goes through these shafts. So the way that's done typically is they will sometimes stuff rock wool in there and put foam on top. Sometimes they'll put spray foam in there, and they might put some spray rubber on top on both sides in order to give it some kind of a fireproof coating. So there's various different ways that you can do that. This is one of my favorite pictures because it shows a facility where they've gone to the effort of putting a fire-rated seal around this insulated line that goes through this wall. But they've lost the context here, because if you look at the top of the sheetrock here, you can actually look into the next room there. So even though they've done a sealing job here, they haven't actually sealed it systematically. In this particular case, this is a laundry room, and that seal would cause the dryers that are supposed to exhaust from the laundry room to pump humid air into the envelope of the building and cause a huge amount of structural damage. So it's a case where one thought pattern and another thought pattern don't coincide. So the idea of compartmentalizing that particular laundry room should have been key in their mind, and actually isolating it from the other air barrier in the building and providing an air barrier for this particular laundry room, which is the only way that you can contain the humidity and the airflows that are necessary to run all the dryers. So this is a case where the engineers actually hadn't really thought through the problem, and when we ran the blower door test on this building, you could see this quite dramatically. So some of the tools that we're talking about here, one is our new Model 300, which comes in a variety of configurations. The one over here is the Model 341, which you use in the U.S. And interestingly, in the U.S., the duct leakage requirements are around about 100 CFM, and Europe they're around about 1 or 2 CFM. And in the U.S., people complain they can't get ducts that tight, and in Europe they seem to be able to get them 100 times tighter than that. So we actually have a very different size of flex duct that attaches to the ducts themselves in the 341, which is the U.S. unit. This is the 351. Both of these units are capable of measuring extremely low flows, and this is our low flow attachment, and this is one that will go down to a few thousandths of a CFM if you want to go that low, and will measure in both directions. This is a different model altogether. This is a commercial duct tester. This is 130 watts. This is 1700 watts. So this particular unit here is designed for testing commercial ducts right up to 5,000 pascals if you want to go that high. And you can see the motor or the blower is like actually hanging out the back end of this particular unit. So 3 different products for 3 different purposes. And here we have our residential fan. This is our new 5000 model, which we're just releasing. It actually has the same fan shell as the one we have now. We have a new nacelle and some other new flow plates on there and so on. So this is what we call house testing fan. It's good for about 5,000 CFM, 6,000 CFM, 8,000 cubic meters per hour, that sort of thing. It does have some limitations, and its main limitation is that it doesn't like back pressure. So at around 75 pascals or so, it starts running out of power. The high power fan that we have over here that runs on a variable frequency drive is quite capable of going up to around 300 pascals, but it will not measure flow over 100 pascals. If we want to do that, we need to go to what we call our contra configuration. But here we have one of the very first ones we've made, and it's 2 fans running in series, and they're running in contra direction, so that the fan in the front is running a 40-degree blade, the fan in the back is running a 30-degree blade, and they're running in opposite directions. If we run them in the same direction, all we do is we get air that just spins around in circles. It doesn't actually drive air forward. This is a configuration where we can turn our blower door into a huge powered flow hood. And in this case, the powered flow hood is being used by Sierra Building Science, who actually manufacture this device, and it's being used to measure air handler flow. So what's great about this powered flow hood is that it can go right up to around about 3,000 cubic feet per minute, much, much higher than any other kind of flow hood. And because it's powered, it's capable of eliminating the pressure drop at the register, so that if we were to use, say, a passive hood in front of this register, then we would actually slow the flow down, we would increase the return leaks and so on. Because we have a powered flow hood here and we're setting the pressure in this hood to 0 pascals, the register doesn't know that it's being closed over, because this fan speed is being regulated, so the pressure on this side of the register is set to 0. There we use our set to 0 function. So here we have our commercial duct tester, which is here being pretty clearly commercial. one of the cool things about it is that often we're in a remote location, we set up the duct tester, we do a test, oops, we fail. So we can walk around with our cell phone, we can turn the thing off, and we can go around, check the seals. One of the seals were leaking, we can tape it up a little bit more, turn it back on with our cell phone, take a reading, turn it off if we haven't passed, and keep turning it on and off with our cell phone so we don't have to keep running up and down the scissor jack to operate the piece of equipment. So really a cool feature that people that do commercial duct testing really like. So I want to open it up for questions. We're at the 11:42 mark, and so I've gone